Welcome to this video on artificial intelligence and machine learning for business, a no-nonsense guide to data-driven technologies as of June 2017. AI and machine learning are now mainstream business tools, applied across many industries to increase profits, reduce costs, and improve customer experiences. Organizations that understand these tools are gaining a competitive advantage. The material in this video is based on the book Artificial Intelligence and Machine Learning for Business by Steven Finlay. Our objective is to cut through the technical jargon and provide a concise, practical introduction for business managers. We focus on how to work with data scientists to maximize results, and we keep things formula-free. You won't find complex equations here, just some basic arithmetic. A simple working definition of AI is the replication of human analytical or decision-making capabilities. A good AI application performs as well or better than the average person when faced with everyday tasks. In practice, AI handles tasks like identifying people in photos, assessing creditworthiness, beating chess masters, assisting via voice-controlled devices, spotting signs of cancer in scans, and powering autonomous vehicles. While it can seem magical, the mystique fades when you look under the hood. It is a mistake to think current AI is conscious. It's ultimately just clever math. Experts agree we are years away from machines with a true human-like sense of self. From a business perspective, most practical applications today are based on machine learning, which for our purposes we can treat as synonymous with AI. Machine learning uses algorithms to analyze data and discover patterns. By identifying these relationships, we can make inferences and take action, like offering discounts to specific customer segments. It is analogous to human learning. We observe the world, draw conclusions, and apply those lessons to future decisions. The final product is a predictive model.
Consider an example where the government wants to identify people at high risk of heart disease to offer checkups within a limited budget. Using historic patient records, they create a development sample of 500,000 cases. Both events, those who developed the condition, and non-events are crucial for the algorithm to differentiate patterns.
The process creates a simple scorecard model. Points are assigned based on characteristics like age, BMI, or blood pressure. By summing these points, we calculate an individual's risk score. The training algorithm determines these point values based on observed patterns in the data.
This distribution table shows how scores translate to real-world risk. By running our population through the model, we can assign each person a probability of developing heart disease. For example, someone scoring 404 has a 1.76% chance over 5 years, based on the observed outcomes of people in that same score range.
How do we use this? If the government can only afford to screen 5% of the population, we use our decision rule to target the highest scoring individuals. In this case, inviting those scoring 521 or higher identifies 62% of all future heart disease cases. This is vastly more effective than random selection, which would only identify 6%. A second example is object recognition. The goal is to identify objects in an image. The principles remain the same. A large development sample containing thousands of labeled images, like chairs or umbrellas, is used to train the system to recognize those specific items. In object recognition, the pixels of an image are the data, similar to medical records in our previous example. With over 65,000 pixels and even a low-resolution image, this requires significant computing power. The underlying logic is similar to our heart disease problem, but the scale makes it far more complex.
For object recognition, the model generates a probability score for every possible object it recognizes. It then selects the object with the highest probability. Effectively, the system predicts the most likely object present in the frame based on these calculated probabilities.
Scorecards are just one type of predictive model. And while some problems require more complex approaches, the usage remains identical. Models generate scores based on data, those scores represent the target prediction, and then you take action. In our next section, we will explore other types of models. Moving on to other predictive models, let's look at decision trees. To calculate a score, we follow a path through the tree based on an individual's characteristics, starting from the top node. At each junction, we choose the branch that fits the data until we reach a leaf node, which provides the final score.
Like scorecards, we use decision trees with a score distribution table. While scorecards use a range from 0 to 999, this tree has 13 discrete endnodes representing 13 possible scores. Different algorithms produce different models, and while the scorecard performed slightly better here, this varies by problem.
Next, let's discuss artificial neural networks. Inspired by the human brain, they link multiple artificial neurons to solve complex problems. While often viewed as mysterious, they are essentially just more complex versions of the models we have already covered. An artificial neuron is just a formula in code. It takes inputs like age or BMI, multiplies them by specific weights, adds them together, and then transforms the result, often using a logistic function, to produce an output score between 0 and 1. A single neuron is surprisingly similar to a basic scorecard model. In fact, a single neuron and a scorecard can be mathematically equivalent. The true power of neural networks comes from combining these neurons into layers to detect more intricate patterns. By connecting layers of neurons, we form a neural network. The output of one layer provides the input for the next. While a simple network has dozens of weights, commercial applications can have thousands. Finding the optimal weights is a computationally intensive task that requires sophisticated mathematics. Neural networks are popular because they can detect subtle patterns that simpler methods miss. However, they are less intuitive. While we can see the math, it is often difficult to pinpoint exactly which input variable is driving the final score, unlike the clarity found in our heart disease scorecard. Deep learning is the evolution of these networks. By adding many more layers, sometimes over 100, we create deep networks. These structures significantly increase the model's ability to identify complex, subtle relationships in massive datasets. Research also considers how neurons connect. Convoluted neural networks excel at image recognition, while recurrent neural networks use feedback loops to process sequential data, like handwriting or language translation. Modern, complex AI applications often combine these advanced techniques. Remember the adage, you don't need a sledgehammer to crack a nut. While complex deep learning is powerful, it is often overkill for simple business problems. In fact, complex models can sometimes find false patterns that don't exist. Always aim for the simplest solution that meets your business objectives. A predictive model alone is not an intelligent application. It just outputs numbers. To add value, it must be integrated into business systems. This involves creating a user interface, pre-processing input data, running the model, applying decision rules, and finally delivering a response to the user. Core components of an intelligent application include data input from various sources, processing that data into a computer-friendly format, applying the model to generate scores, and then using both models and human-defined rules to make an automated decision. Let's look at two deployment examples for our heart disease model. A doctor's selection tool might run in the background on a database, while a patient self-diagnosis tool would require a phone app interface to capture speech and provide immediate verbal health guidance. Sophisticated applications often use multiple interacting models. For example, a speech-to-text model could translate spoken input into the format required by our heart disease predictive model. Many of these foundational components, like speech recognition, are now readily available off the shelf. Remember that business users shouldn't focus on technical accuracy metrics like Gini coefficients. What matters is the bottom line: profits, costs, and time saved. If a data scientist can't express the value of their solution in terms of your business objectives, they have not yet succeeded. When implementing AI, organizations must consider the human impact. Will your machine learning project result in redundant roles or de-skilling? It's essential to plan how the organization will manage these transitions and the resulting change in daily tasks. Ethical and legal considerations are also critical. Machine learning models have no inherent social awareness or conscience. They simply find patterns. If those patterns are based on sensitive factors like gender or ethnicity, they can lead to bias, which poses significant legal and reputational risks to your business. It is easy to get excited about the math behind predictive models, but never forget you are trying to solve a specific business problem. A highly accurate model has no intrinsic value unless it is applied to a real-world task. Implementation is often more expensive and time-consuming than the actual model development. When building your project team, do not just hire a data scientist and expect them to deliver a solution in isolation. Just as you need an architect to design a building, you need project management to ensure the AI solution aligns with your business requirements and delivers the intended outcome. Data scientists have a specialized skill set focused on mathematical aspects, but they may lack deep institutional knowledge of your business. For any large-scale project, define your requirements and measures of success clearly at the outset, and hold regular project meetings to keep the team on track. Before moving past the feasibility stage of any project, use a formal checklist. Ensure all questions regarding business goals, data availability, and ethical risks are captured in your project requirements. This simple preparation is key to long-term success. Your checklist should cover several core questions. What is the specific business problem? What metric, like cost reduction or profit, are you optimizing? What actions will you take based on the model's predictions? And how will you ensure the required data is available operationally? Consider the operational life cycle. How will you implement the model? Who will maintain it? And what are the ongoing costs? You must also monitor the system to ensure human staff are following the model's recommendations, or if overrides occur, that they are justified and correctly monitored. Finally, define how you will measure success. The theoretical benefits during development are just indicators. Real-world success requires a monitoring process to compare actual outcomes against your original business objectives, ensuring the project delivers real value. The appendix provides a glossary of common terms, from activation functions, the math that transforms a neuron's output, to algorithms and big data. Understanding this vocabulary helps bridge the gap between technical data scientists and business management. Key concepts like classification versus regression models, supervised versus unsupervised learning, and the dangers of overfitting are essential knowledge. These terms define how models learn, how they make predictions, and why validation samples are so important to prevent misleading results. All right, here's some vital terms, including Gini coefficients for accuracy, decision rules for taking action, and ensembles like random forests. These tools allow you to evaluate and refine your models so they perform reliably in real-world environments. Thank you for watching this overview of artificial intelligence and machine learning for business. We hope this guide helps you navigate these powerful technologies to drive real, data-led success in your organization.